Let's have a seat. We're going to continue where we left off last time. And we started talking about the properties of the Fourier transform. So let's keep on going down the list. The next one is called time shifting property. This one says if f of x of t has a Fourier transform x of f, then x of t minus some t0 will have a Fourier transform x of f e to the minus j 2 pi f t0. Let's demonstrate that this is a case, and then discuss briefly the physical meaning of what this property says. Let's take a look at Fourier transform of x of t minus t0 is integral when t goes from minus infinity to plus infinity x of t minus t0 e to the minus j 2 pi f t dt. Right, that's just a straightforward application of what the Fourier transform formula is. Now we're going to introduce this substitution. T minus t0 is equal to nu. Therefore, dt is the same as d nu, and tb can be expressed as nu plus t0. So now this integral here becomes, when t is in minus infinity, where is nu? The nu is in minus infinity as well. So nu goes from minus infinity to plus infinity. X of nu e to the minus j 2 pi f. And instead of t, I have nu plus t0, and then d nu. Right, just doing the substitution. And now you see here that there is e to the minus j 2 pi f t0 that does not depend on nu, so it can be taken outside of the integral. So this becomes integral when nu goes from minus infinity to plus infinity, x of nu e to the minus j 2 pi f nu d nu, and then everything here multiplied by e to the minus j 2 pi f t0. Do you recognize the term here in parentheses? This is x of f, right? The Fourier transform. So this is equal to x of f e to the minus j 2 pi f0, f times t0. Now, let's say a couple of words about the significance of this physics. When I'm delaying the signal in a time domain, do I need to change the sines and cosines that I use to build this signal? No, they're going to be exactly the same sines and cosines. Everything is going to be shifted in time. So by shifting sine and cosine in time, what I'm actually doing is I'm shifting their phase. Therefore, the magnitude of the magnitude spectrum of a signal that's shifted in time does not change. Right? It's the very same sinusoidals, and it's in the very same proportion that I need to add them. What changes is their phases, because I need to now align them with the reference to a different time. And that's why there's a change in a angle spectrum, or in the phase spectrum, and not a change in the magnitude spectrum. Frequency shifting property, so that's the number 5. This one says if x of t has a Fourier transform x of f, then x of t e to the j 2 pi f0 t has a Fourier transform x of f minus f0. In other words, the Fourier transform of a signal multiplied by this complex exponential here is essentially the translated signal in a frequency domain. This one can also be demonstrated very easy. The Fourier transform of x of t e to the j 2 pi f0 t is equal to the integral when t goes from minus infinity to plus infinity x of t e to the j 2 pi f0 t, and then times the kernel of the Fourier transform minus j 2 pi ft dt. That's just straightforward application of the definition. So now I have integral when t goes from minus infinity to plus infinity x of t e to the minus j 2 pi f minus f0 t dt. And you see right away that this is a Fourier transform, but instead of f, I have f minus f0, okay, which is equal to x over of f minus f0. The next one is really, really important, and it's called modulation problem. Here's what it says. If x of t has a Fourier transform x of f, then x of t times cosine 2 pi f0 t has a Fourier transform 1/2 x of f plus f0 plus x of f minus f0. Okay? So how do we demonstrate this one? Well, if you look at the left-hand side, x of t times cosine, let's put here proof, cosine of 2 pi f0 t can be seen as x of t e to the j 2 pi f0 t plus x of t e to the minus j 2 pi f0 t divided by 2. How did I obtain this? Well, cosine is e to the j plus e to the minus j over 2, and I just brought x of t inside. Now, if I use the previous property, which is my frequency shifting property, I see that the first term is 1/2 x of f plus f0. Why? Because you see here, first term is minus f0, and then this one here is plus 1/2 x of f plus f0. So just utilizing previous property, I get the proof of this one. Why is this one important? Because it tells us how we can actually translate the spectrum of the signal pretty much anywhere along the frequency axis. If you look at, if I were to draw this, and I'm just going to draw a magnitude spectrum. Let's say this is a magnitude spectrum of my signal, x of f magnitude, and let's say it occupies some bandwidth from minus w to plus w. Then if I multiply my signal with the cosine, what it does in the frequency domain is it performs a translation of the spectrum of the signal, and it centers that around the frequency f0. So here's my signal 1/2 x of f minus f0, and here's the signal 1/2 magnitude of x plus f0. So what I did is, by multiplying the signal with the cosine, I have moved the frequency content of the signal, the sinusoidals that are building this particular signal, from one place along the spectral axis to the other place in the spectral axis. This is a very, as I said, very important property. It's actually a fundamental property for many of that is used in many communication systems. One of the part of the a significant part of any communication system is the modulation part. And frequently through modulation, we move the frequency content of the signal to a different frequency, and we usually call this carrier frequency, where where the signal is now centered there. So one more property, also extremely important. As a matter of fact, from the standpoint of the linear system, it's just about the most important property. It's called convolutional property of the Fourier transform. And I frequently say, if we were in the circus, right, this would be the main act. This is the main reason why we use Fourier transform so frequently as we do. So let's just go through this one and make sure we understand what is happening. All right, so convolution problem. We have two functions. One of them we call x of t, and this one has a Fourier transform h of f. The other one we call h of t, and this one has a Fourier transform h of f. Okay? Then the Fourier transform of x of t in convolution with h of t is equal to x of f multiplied h of f. Okay? So we already know that this is very significant, because what happens just in the outset, what we see here is that Fourier transform turns convolution into multiplication, right? And we already know that convolution is a relatively complex operation that, to evaluate. Multiplication is just as simple as you can. So if we can, what a Fourier transform does for us, it saves us from convolution, right? And it's a very noble thing. Right, so let me prove this. So let's say Fourier transform of x of t convolved with h of t is, let me just see how, well, integral when t goes from minus infinity to plus infinity, x of t convolved with h of t, and then we have e to the minus j 2 pi ft dt. Just a straightforward application of the definition here. But then this middle part is also an integral. So the whole thing is integral when t goes from minus infinity to plus infinity. Integral inside is tau goes from minus infinity to plus infinity. X of tau, h of t minus tau, d tau. And then this needs to be multiplied by e to the minus j 2 pi ft dt. Right? What did I do? Nothing smart. I took this middle part that's in the bracket and I replaced that with the expression for the convolution. And then what we do in this case, just like in many similar cases, we're going to change the orders of the integration. We're going to integrate first with respect to t, and then on the outside with respect to tau. So if we do that, we obtain the following. Fourier transform of x of t convolved with h of t is going to be integral when tau goes from minus infinity to plus infinity. X of tau does not depend on t, so it goes outside. So it's x of tau. And then we have all the things that depend on t inside. So this is integral when t goes from minus infinity to plus infinity, h of t minus tau, e to the minus j 2 pi ft dt, and then everything at the end d tau. Okay? Now, if you look at this, this is what? This is a Fourier transform of the delayed version of h of t, right? If I know how do I obtain the Fourier transform of the delayed version? I have to take the Fourier transform of the signal and multiply that by e to the minus j 2 pi f t0. So this becomes an integral when tau goes from minus infinity to plus infinity, x of tau and this is now h of f e to the minus j 2 pi f tau, and then d tau. Where is this coming from? This is this delay, t minus tau. So if the signal is delayed by t minus tau, its frequency response is multiplied by this term here. And this just tells us that there's an additional phase shift. This is the first thing that we went through today. So now, h of f does not depend on tau. It goes outside. And then you have integral when tau goes from minus infinity to plus infinity, x of tau e to the minus j 2 pi f tau d tau. What is this? This is the Fourier transform of x of t. So this is h of f times x of f. Okay? So these are the most significant properties. I'm sure you've seen some of them, if not all of them. You know, there are other properties, and I think your book gives other properties too. But I tried to cover the main ones. What is important here is to realize what are some of the physical meanings behind these properties. Like it is very, this one we're going to spend some more time to get to its exact physical meaning. But the property that says, okay, if I delay the signal, I'm not changing the magnitude spectrum. You know, you kind of need to understand these kind of properties on a physical level, right? So that it's not just formulas that are you know, that you kind of copy from a piece of paper.
So let me give you. I have a question here. But the convolution property, is it like to change the time domain signals to the
Frequency domain?
Yeah.
Yes. Let me give you. That's the next thing that I'm going to explain. You know,
Oh, okay.
essentially, we're at on the brink of a pretty fundamental discovery, right? And I'll just talk about it in just a second. But let me give you the problems that exercise this. So problems are 7, 1, 1, 7, 1, 2, 3, 4, 5, 8, 7, 2, 1, and 7, 2, 2. So those are the problems that cover this kind of material. So going back to your question, it's the question is this like frequency domain and time domain? It's exactly like that. So here's the picture that where we that is very important to us. Here's our linear system, right? And so far we've been describing a linear system by its impulse response. We said if I know impulse responses of the system, I know everything I need to know. If you give me any kind of input, I'll be able to predict the output by taking the convolution of your input signal with the impulse response of the linear system. So in the time domain, here is the story. I have x of t presented to my linear system, so this is linear system. And I'm able to always calculate y of t as x of t convolved with h of t. And this is our time domain. Now, let's look at what we have uncovered by introducing the Fourier transform. This h of t can be transferred into, this x of t transfers into x of f. What is x of f? X of f is the Fourier transform of your input signal. This h of t transforms into h of f. And this y of t transforms into y of f. And then this y of f is simply h of f times x of f, which is, oh, sorry, h of f. So, which is a much easier thing to evaluate. And it also tells us how does this linear system operate on an input signal. Here it is a little bit difficult to see the bed. And remember, but you should remember how we derived this. We said, well, what I'm doing in a time domain, I'm seeing the signal as a whole bunch of impulses. Each impulse is producing an impulse response, and therefore the overall output of the system is sum of all of these impulse responses, right? So that's the interpretation of this result. Here, I'm seeing this differently. I'm saying, okay, each signal is built out of sinusoids. I put my Fourier glasses, and I see my signal not now as a time domain waveform, but as a whole bunch of sinusoidals that happen to align themselves in a particular way to form the signal, right? So the signal is just a bunch of sinusoidals. Now, my linear system is an operator on each one of these sinusoidals. What I know from linear system theory is when I present a linear system with a sinusoidal, what is it that I get at the output? I get a sinusoidal of the same frequency, potentially different magnitudes in phase. And what this teaches me here is that linear system actually operates on one sinusoidal at a time, right? It takes the sinusoidal, changes its magnitude in phase, moves to the next one, does the same thing, moves to the next one, does the same thing. And the effect is that this multiplicative effect, right? This is a complex multiplication that says, take a sinusoidal, change its magnitude, and change its phase. And then, really, the spectrum of the output signal is the same as the spectrum of the input signal in terms of which sinusoidals are there, but they're rearranged in a different way. They may have slightly different magnitudes and different phases. But there are no new sinusoidals. That's a fundamental property and fundamental test for the linearity of a given system. From here, it is very apparent that the linear system cannot produce sinusoidals of a different frequency. All it does, it multiplies and changes the ones that are already there. No new ones can be produced.
Can we take it as a test? Like we always do the frequency analysis of the output and
This is one of the principal tests. We have what we call single tone test and two-tone test. And these are the tests that are used to determine how linear your device is. And no device is perfectly linear. But what we do is we put two sinusoidals. We know that I should get those two sinusoidals back. But as a testament that no device is linear, I'm going to get some other sinusoidals. And the most frequently used measure of how linear a particular device is the ratio in the power of those sinusoidals divided by the ratio of the power of all these parasitic components that result from the system not being linear. And in a good, for example, linear power amplifiers, this can be 30, 40, 50 dB, right? So much, much larger, right? So that means that for all practical purposes, the system is linear.
Can we do the inverting system? Whenever I have like the frequency domain signals, can I invert that into the time domain signals?
Yes. Yes. As a matter of fact, you can do. Let's say objective is to determine the output of the signal, output of the linear system to give an input. One way to compute is this, right? I'm given an input. I know what the impulse response is, and I can calculate the input straight by doing convolution. Most commonly, actually, even though it seems longer, we do it this way, right? We take the Fourier transform of the input, take the Fourier transform of the impulse response, determine the Fourier transform of the output, and then if necessary, we go back. A lot of times we can actually stay here and conclude whatever we need to conclude just by looking at the frequency response or the Fourier transform of the output signal. Right?
So are doing any significant change of the sinusoidal signals in the output?
Yeah,
Like you have like
depends what this filter is. This filter may kill some sinusoidals.
Oh.
Let's say if it's a low-pass filter, it can kill all the sinusoidals that are above certain cutoff frequencies. So it can change the spectrum. The point here is it cannot bring new sinusoidals, right? The sum of them may disappear, but no new ones can appear.
So can't be its own noise can produce some another sinusoidal signal?
Say again?
It's the noise of the filter noise,
Uh-huh.
its own noise, that can produce a new sinusoidal signal?
Yeah, I mean, noise is made out of, especially white noise is made out of all sinusoidals, right?
That's why
So-
you have SNR.
But that's not, linear system, you know, on its own does not have noise, right? We model noise outside. All right, so let's look at a couple of other properties. One is time differentiation and time integration. If x of t has a Fourier transform x of f, then derivative dx of t over dt has a Fourier transform j 2 pi f times x of f, and integral from minus infinity to t x of tau d tau has a Fourier transform 1 over j 2 pi f times x of f, and then plus 1/2 x of 0 times delta of f. So, in other words, if I know the Fourier transform of the signal, obtaining the Fourier transform of its derivative and its integral is a relatively straightforward math. And we use these two properties quite often to, you know, calculate the Fourier transforms of signals. Sometimes it is easier to, for example, get the Fourier transform of the derivative, and then once you have the Fourier transform of the derivative, you get back the Fourier transform of the original signal. So let's prove this one. So let's call this one A. This is A, and this is B. So I have x of t has a Fourier transform x of f. Then Fourier transform of the derivative dx of t over dt. By definition, this is an integral when t goes from minus infinity to plus infinity dx of t over dt. And then I have e to the minus j 2 pi ft dt. Nothing smart here. All I did is just replace this symbol Fourier transform with the actual integral. Now, we're going to integrate this one by parts. I'm going to say that u is equal to e to the minus j 2 pi ft. Therefore, du is going to be equal to minus j 2 pi f e to the minus j 2 pi ft. And I'm going to say dv over dt is equal to dx of t over dt. Therefore, v of t is equal to x of t. And my Fourier, so therefore the Fourier transform of the derivative is equal to u times v, which is this times this. So x of t e to the minus j 2 pi ft from minus infinity to plus infinity, and then plus integral from minus infinity to plus infinity v du, which is x of t times this. So it's j 2 pi f times x of t e to the minus j 2 pi ft dt. Okay. So it's u times v, so this times this, minus v du, but because of this minus it becomes plus here, and then here's v du. Now, x of t is a signal for which I have a Fourier transform. That means that the signal is is, equal to, is equal to 0 at minus infinity and plus infinity. Therefore, this part here is equal to 0. And then you end up that this is j 2 pi f, integral from minus infinity to plus infinity, x of t e to the minus j 2 pi f t dt. And you recognize that the second integral is essentially x of f. So I get that this is j 2 pi f x of f. So taking the derivative in a time domain is in a frequency domain is equivalent to multiplication of the Fourier transform of the signal by this j 2 pi f. Now let's think about what does this mean. This tells me that taking a derivative is essentially a filtering operation. It's a linear filter, right? It's a filter that has a frequency response given as j 2 pi f, right? And this whole differentiation in a time domain is essentially equivalent to modifying the frequency content of your signal by multiplying everything with j 2 pi f. Okay. So, okay.
Can we state that by differentiating a signal, we are making it an imaginary one because the j is coming in
No.
frequency domain?
How are we making it an imaginary?
In frequency domain, we got like j into 2 pi f.
But this is a complex number too. Right, this is a plus jb. So that this whole thing has a real and imaginary part altogether. Right? It is multiplying the magnitude by 2 pi f, which means that the higher frequencies are multiplied more, their magnitude increases, and it's introducing a phase shift of pi over 2 to each sinusoid. Right? That's what it's doing.
Regarding his question, so it means that the j 2 pf should be the magnitude should be in integer.
Why?
Because
Why?
the
It's
magnitude changes the
what?
phase.
It changes the phase. This can be written as 2 pi f e to the j pi over 2. So it's taking every sinusoidal and it's changing its magnitude in proportion to its frequency. So the higher frequency sinusoidals are amplified more, and it's adding the phase shift of pi over 2 to every one. Okay, that's what it does. Let's look at the part B. Part B, we have that x of t has the Fourier transform of x of f. Then Fourier transform of an integral, which is minus infinity to t, x of tau d tau, is equal to integral when t goes from minus infinity to plus infinity. Integral tau goes from minus infinity to plus infinity. X of tau d tau, and then everything e to the minus j 2 pi f t dt. Right? What did I do? Nothing really smart. I substituted this for a function, and then I have this double integral. And let's take a look at this integral here in the middle. So integral when tau goes from minus infinity to plus infinity, x of tau d tau. I can see that this integral when tau goes from minus infinity to plus infinity, x of tau times z of t minus tau d tau, where z of t minus tau is equal to 1, right? In other words, artificially I can see this integral here as a convolution, right? of the convolution between the signal x of tau and signal which is equal to 1. Okay? Now, we know the following. We know that Fourier transform of x of t is equal to x of f. And Fourier transform of 1 is going to be equal to 1 over j 2 pi f plus 1/2 delta of f. That's in your table of Fourier transforms. So now I can see this thing here as a Fourier transform of the convolution between this x of tau and z of t minus tau. Fourier transform of the convolution is the product of the Fourier transforms. So in a straightforward manner, I can write that this is x of f times the Fourier transform of 1, which is 1 over j 2 pi f plus 1/2 delta of f. And this is simply x of f over j 2 pi f plus 1/2 into 0. Which was, and I can put delta of f. Actually, I have to put delta of f to indicate that this only exists at 0. So if I know the Fourier transform of the signal, I know the Fourier transform of the integral of that signal. It is for the most part h of f divided by j 2 pi f. But if signal ends up having a DC component, then there is this term here that I need to add at the very end. Okay? So in your book, there's a table 7.2 that gives you some important Fourier transform properties, right? Even beyond what I've covered in class. Some of them you're going to be using all the time, so you know them by heart. Some of them you may need to resort in some special cases when you try to evaluate the Fourier transform of some signals. Let's illustrate some of this. As a matter of fact, let's illustrate this property A through a simple example. I'm going to look at an example. This is same as your 717 in the book. It says use time differentiation property to find the Fourier transform of a triangle pulse. So I have a pulse delta t over tau. That's a notation that we use in this book. And how does this one look like? It's a pulse. It's a triangular pulse. It looks like this. It stands from minus tau over 2 to tau over 2. Therefore, the base here is tau. And the height here is 1. That's a delta of t divided by tau. So how does the derivative of this one look like? Derivative of delta t tau divided over dt. Remember, the derivative is the slope, right? So this one exists from minus tau over 2 to tau over 2. What is the slope in this interval? What is the slope? You advance 1 over tau over 2, right? So the slope is 2 over tau. Actually,
y by x, 1 by minus 2. So minus 2.
no, the slope here is you go from 0 to 1, so 1 over the interval over tau over 2. So the slope is 2 over tau, right? If tau is equal to, let's say tau is equal to minus 2, then this is from minus 1 to minus 1, you get to 1, so it will be 1. Right? But in this general case, this is 2 over tau. So the slope is positive here. How about here? is the same thing, just negative, right? So it is minus 2 over tau. So this is how the derivative of this triangle look like. It is these two pulses that one of them is positive and one of them is negative. Now, how does the double derivative? The second derivative of this look like? Well, this one is for the most part constant, right? Except at the transition. So there's a delta pulse here, right? That has that is 2 over tau delta. It's right here. It's 2 over tau delta of t plus tau over 2. That's the pulse that exists at this edge. Then I have, I'm just going to put 0. Then I have a pulse that goes down. This is 4 over tau, minus 4 over tau, delta of tau. And then you have another pulse that goes up. That's 2 over tau, delta of b minus tau over 2. So we started with triangle that's shaped like this. And you know, you could do straightforward evaluation, but then you have some integrals to compute, right? Then you say, well, let me see what the first derivative looks like. And the first derivative are these two square pulses, right? The first pulse is for this section of the triangle, and the second pulse is for this section of the triangle. And then you take the derivative of this. Derivative before minus tau over 2 is 0, right? Derivative between minus tau over 2 and 0 is also 0. The function is constant. So the only derivative that you have is this edge here. And the derivative of this edge of the step function is the delta function. So there's a delta function with a magnitude of 2 over tau, and it's centered at minus tau over 2. There's another delta that goes from here down here. So that one, the magnitude is 4 over tau, and it's centered at 0. And there's a third edge that goes from here to here. The magnitude is 2 over tau, and it's delayed, and it's centered at the place of the tau over 2. Now that I have this guy, the Fourier transform is trivial, right? The Fourier transform of the delta, we always like integrating delta pulses, because there's really nothing to integrate. You're essentially just sampling the subintegral function.
Excuse me, Professor.
Go ahead.
Why whenever you derivate that from the delta of t over tau, the signal looks like the discrete signals?
Correct.
The delta.
Because it's step function? Something like that? Because it's delta function?
Yeah, I mean, what's wrong with that? I mean, signal is not discrete. It looks like discrete, as you said, but it's not discrete. It has a value at every point. What's the value here?
Average of those two.
What is the value here? 0, right? So it is defined for every single tau, for every single t, right? Every single. It just happens to be 0 most of the time, except these 3 points, in which case is infinite, right? But the area and the curve is finite, it's finite. But the signal it looks like a discrete, because that's how I draw it. So now, what's the Fourier transform of the second derivative? So Fourier transform of d squared of delta of t over tau over d t squared is the Fourier transform of these guys, right? But I also know this, that the Fourier transform of the second derivative is j 2 pi f times delta of f. Right? This is based on my previous formula. So now, by applying this, let's say this thing here, I have Fourier transform of d squared of delta t over tau over d t squared is equal integral when t goes from minus infinity to plus infinity, and I can write this out. So this is 2 over tau delta t plus tau over 2 plus, or actually minus, 4 over tau delta of tau, and plus 2 over tau delta of t minus tau over 2, and then everything e to the minus j 2 pi ft t. Right? One thing I know is there's this square here, right? One thing, this is one thing I know, and this is, I can evaluate this, if I can find this Fourier transform, then just by setting the left-hand sides that are already equal, setting the right-hand sides to be equal, I can easily calculate delta of f. The Fourier transform of this thing here is extremely easy. It is 2 over tau, and then evaluate of this function at this delta. So this is e to the minus j 2 pi f delta, actually plus delta over 2, minus 4 over tau, and then plus 2 over tau, e to the minus j 2 pi f tau over 2. Okay? That's the Fourier transform of this integral function here. And then you can easily see that this is already some form of cosine. So I can write by setting that this is equal to this, I can say the delta of f is equal 1 over j 2 pi f squared. So this is this dividing, and then I can set this to be put extra minus outside, and this is 4 over tau minus 2 over tau, and then I can have e to the j 2 pi f tau over 2 minus, or rather plus, e to the minus j 2 pi f tau over 2, and I need 1 tau, 2 there, and another 2 here to make it a plus. So let me explain the steps here. If you look at this is equal to this, right? So equate the right-hand side. This is equal to this, and then take both sides and divide by j 2 pi f quantity squared. So you have delta f 1 over j 2 pi f quantity squared. I put the minus 1 outside because I want to make this one positive and these two other negative. So I have 4 over tau, 2 over tau, and then I have 2 here and 2 here that obviously I'm trying to make a cosine. So this simplifies. Notice this j squared and minus 1, they cancel each other, right? Because j squared is minus 1. So I have 1 over 2 pi f quantity squared. Now, look at here, 4 over tau, 2 over tau times 2. So I'm going to take 4 over tau outside. So this is 4 over tau outside. And then I have 1 minus cosine 2 pi f tau over 2. So it's 1 minus cosine pi f tau. What is 1 minus cosine? It's a sine squared, right? Of 1/2 of the angle.
Yeah.
So I can rewrite this yet one more time to make it, let's make sure that so here this 4 and 4 will cancel, and I can write this as 1 over pi squared f squared times tau downstairs times sine squared pi f tau over 2. And one more step. I'm going to say that this is tau over 2. So I pull one tau outside, so I have tau squared downstairs. And what I'm left with is sine squared of pi f tau over 2 over pi f tau over 2 quantity squared. This should work out somehow. There's 2 missing. 1 minus cosine is 2 sine squared. Right? And now I get that this is delta of f is tau over 2 sin of pi f tau over sin squared. Thank you. Sin squared. So the Fourier transform of the delta of a triangle pulse is sin squared. You can do that many different ways, right? We could have integrated at any point here. I could have integrated here directly. I could have integrated here, but what I needed to do at the end, divide by j 2 pi f. But I decided to integrate at this point and divide by j 2 pi f squared. Right? So just an illustration that you can actually do evaluation of the Fourier transform of the function by looking at the Fourier transform of its derivatives and its integrals as well. Any question here? I made that point last time, just to make clear. Sinc is defined in your book. Sinc of x is defined as sine of x divided by x. This is the definition in the linear system book. In most books, alternative definition. Particularly in most communication books, sinc of x is defined as the sine of pi x divided by pi x. To make the distinction, your book calls this one sinc pi of x. Right? So that you know which one it is. Then nothing really sparkly, just be careful. And not in this book, be careful in every book to know exactly what they mean when they say sinc. Okay, so we have a lot of math here. Let's spend some time trying to understand a little bit about the physics behind it. So this is how do we understand some of these results here. Let's first look at what we have. Here's what we've learned thus far. We have a linear system and we saw that we can work around this linear system in either time domain or a frequency domain. If I stick to the time domain, I'm looking at the time domain input, I'm looking into impulse response of the system, and I'm getting my output as x of t convolved with h of t. If I choose to work in a frequency domain, then equivalent would be h of f, which is the Fourier transform of my input signal. The description of h of t will be given through h of f, which is the Fourier transform of the impulse response, which we call frequency response. Right? Fourier transform of the impulse response is a frequency response. And I know that I can obtain the Fourier transform of the output signal as h of f times x of f. The key thing here is that this is much easier to evaluate than the first one, because we are working we're just multiplying things instead of taking the convolution. Now let's take a little bit more in-depth look. So time domain. Here's our understanding of it. Delta of t produces h of t. Right? If I hit this linear system with a delta pulse, what will come out of the system as a result of this delta pulse is going to be the impulse response, h of t. Now, x of t, my input, I can decompose as integral when tau goes from minus infinity, plus infinity, x of tau, delta of t minus tau d tau. In other words, the way how I can see the input is a whole bunch of pulses coming one after the other, or an alternatively, I can see the input as a convolution between x of t and delta pulses. When you convolve the signal with delta pulse, you get the signal back. Now your y of t is integral tau goes from minus infinity to plus infinity, x of tau, and instead of this delta, I have h of t minus tau, delta of tau. This is the superposition theorem at its best. It says, if I decompose my input as sum of the delta pulses, my output is going to be sum of my impulse responses. Right? And that's how the time domain operates, right? How do we think in a time domain? Let's look at the frequency domain. Now, here I put infinite exponential j2 pi f e, and I know that the response of the linear system to the infinite exponential is h of f e to the j2 pi f t. So what I find out is that the response of the system to the infinite exponential is more or less trivial. What I get at the output is the same function that I put in, just shifted in magnitude and phase, shifted in phase and possibly scaled in a magnitude. This h of f is a complex number. It will change the magnitude of this signal, and it will add to its phase. So now, I look at my Fourier transform in a different light. What is the Fourier transform? It's an integral when t goes from minus infinity to plus infinity, x of t e to the j 2 pi f t dt. What you see here is that this is essentially sum of these exponentials. I have decomposed, I have represented my h of f as a sum of scaled exponentials here. Therefore, my y of f is going to be sum of the responses. So this becomes, sorry, I messed up here. I can say x of t is equal to integral when f goes from minus infinity to plus infinity, h of f e to the j 2 pi f tau d. So I'm saying that my input signal x of t is sum of these individual exponentials. I'm saying this is an exponential. Think of this s as a sum. Every exponential at the frequency f is multiplied by appropriate magnitude, and there's a phase added to it. And then I sum all of these exponentials to form my x of t. I know the response to every one of these exponentials, right? Every one of these exponentials, when presented to the linear system, will result in the same exponential, just scaled properly. So my y of t will have to be integral when f goes from minus infinity to plus infinity, h of f times x of f times h of f e to the j 2 pi f t dA. In other words, you look at this, produces this, right? And because of the superposition, now I saw my signal as in this expression here, as the sum of a whole bunch of exponentials. Then at the output, it's going to be sum of all the responses to these exponentials. And the exponential has a trivial response where it goes through the system unchanged in frequency, but changed in the magnitude and phase. Now, so what you see here is that my output is essentially h of f times x of f times h of f inverse Fourier transform. So that's where we get that y of f has to be h of f times x of n times h of n. This is the same as convolution property of the Fourier transform. So, two decompositions, one of them done in a time domain. I'm decomposing the signal as a bunch of impulses, and my output is the sum of the impulse responses. Here, I'm decomposing the signal as a bunch of exponentials, and my output is the sum of the responses to those exponentials. Go ahead.
Excuse me, Professor. Can you give us actually the real practical idea whenever we got the signals in the real life? Which one we need to do the time domain, which one we need to do the frequency domain? It means like the Fourier transform signals.
Can I give you practically? You have to be able to switch back and forth like this. It's not like, you decide and let me do this one, let me do the other one. A lot of times you're going to be doing both of them and simultaneously, right? So the thing is, here's the reality of it. There are these two worlds, right? One is the time domain world, and the other one is the frequency domain world. They are both very real. They exist, and everything that happens in this world happens in the other one too, in terms of signals. We just happen to live in time domain world, but there's another, on the other side of the mirror, there's a frequency domain. Everything that occurs in this one has its equivalent in the other one. Like if I filter in a time domain, I filter in a frequency domain. If I translate in a time, modulate, demodulate, whatever I do in a time domain, there's an equivalent operation in a frequency domain. Sometimes it's easier to see in a time domain, but that's very rare. Most of the time, the clear understanding of what is actually happening, we gain from looking at the frequency domain. So, to answer your question, taking the Fourier transform of the signal, it's cool, but it's not very important. Why would you want to take the Fourier transform of the signal? Let me go do something better, right? What you actually do is you do things like you design a system, right? And you want the system, for example, let's say you design an audio system, and you want a system to, let's just look at a very, very simple example. Let's say you're listening to your stereo in a car, and every single person has a different flavor. What is it that they like in music? Some people like more treble, some people like more bass, some people listen to guitar, some listen to drums. You listen to all of these things. Now, how do I design the system to cater to those people? And the thing is, okay, can I do it in time domain? Probably. But easier to understand is if I think about all of this in a frequency domain. And if you think of this in frequency domain, it becomes really clear what you need to do. Drums, they live in a low part of the spectrum. Bass lives, 50 to 200 hertz. Guitar is 100 hertz to, let's say, a couple of kilohertz. Then you have cymbals, whatever is. So they're all kind of, even though they overlap, they occupy different portions of the spectrum. So what is our solution to this problem, to this design, where we're going to build a bunch of filters that are going to look like this, that are work in a frequency domain and allow user to adjust the magnitude for each one of these filters, right?
But whenever you have, excuse me, but whenever you have the frequency domain, there will be a threshold, right? Whenever you have it, am I correct?
Threshold for what?
For the result, for the output of your system.
You are not considering the harmonics.
Yeah, the harmonics too.
No, these are linear filters, right? And this is what I drew here is a 4-band equalizer, right? And know that a lot of equipment comes with the equalizer, right? If you look at your stereo, you have ability to adjust
1 kilohertz, 20 kilohertz, something like that.
There you go. So even though we live in a time domain, what is actually the easiest way how we understand this particular problem and propose the solution is by looking at the frequency domain. So if you say, if I want to hear more bass, let me amplify this portion of the spectrum that is between 50 and 200 hertz, right?
Right.
And then you go and you adjust that, or you may have a knob that turns, a lot of cars, they have just a bass and a treble, right? Just the lower frequencies and higher frequencies. This is a 2-band equalizer. But sophisticated musical equipment, you can have up to 16 bands or even more.
8-band equalizer and
Yeah.
then 12-band.
Yeah. So that's an example. So it's not like that you're going to be taking Fourier transform of various signals. You don't go through life and say, oh, here's a signal, let me take a Fourier transform, right? No, you have a problem like this, and you say, okay, how do I approach this problem? If I approach in a time domain, I don't even know where to start. But if I approach it in frequency domain, it is very easy to understand what I need to do. I need to allow user to adjust different portions of the band, the magnitude response of my system to different portions of the band. This is one problem in which the solution is in a frequency domain. There are other problems where frequency domain makes no sense, but the time domain is where you search for the solution. At this stage, we should not worry too much about it. This comes in a later course. At this stage, you are building tools, right? So you have to understand all of these for the sake of understanding these particular tools, right? And then when you move into communication theory, when you move into control systems, adaptive filter theory, image processing, signal processing, all of these would actually use these tools that we have developed. All right.
Brilliant answer. I like that.
Well, you kind of know that you're getting old when even the shortest questions lead to these long answers, right? All right, so, okay. So let me talk about, just define what, and then we'll pick up the next time. Here's the problem, and it's actually another very good example of what you just asked. The problem is posed in a time domain, but we're going to actually present the solution in a frequency domain. This is called distortionless transmission of the signal. Let's say I have a linear system and I present the signal x of t, and this is h of f and equivalently h of t. And I get my signal y of t, or what we learned, this can be y of f, if you look at this in a frequency domain. This linear system here, I put it as a box. But usually, it consists of multiple blocks that are chained together. Let me give you an example. Let's say I can look at the whole system from the microphone all the way to the speaker as a one system, right? That consists of a whole bunch of things that are cascaded together. It is of great importance to understand, well, what are the properties of this system so that what comes out of it is the same as what I put in. That's called distortionless transmission. That's a problem that we have, fundamental problem of the communications. I want to say something here, and the microphone captures what I'm saying, and this is replayed half a world away, and I want to make sure that I understand what needs to happen so that what is replayed over there is the same as what is being produced here. What kind of properties does this system have to have, right? So the short answer to this long question is we say that the transmission is distortionless. If this y of t is equal to some gain x of t minus t0. In other words, if there is some scaling to the signal, I'm okay with that, because I can, crank the volume or lower the volume. So I can assume that the gain here does not introduce any distortion to the signal. And also, I'm going to allow a delay, right? Because the signal travels long distances or short distances, whatever may be the distance. But if there is a delay introduced in a whole signalless group, I'm going to assume that the signal is delivered to the reception point without any distortion. So my linear system that is distortionless has to produce the signal y of t at the output, which is scaled and possibly delayed version of the input signal. What kind of properties this linear system need to have? That's the question we need to answer. And what we're going to do, we're going to formulate it in a frequency domain. The view from frequency domain, as in many other cases, is going to be much more clear. But that will follow next time. Right? So I don't want to I want to leave you in suspense until Thursday.
But my answer